All right, Mr. Turk here. I'm going to try to provide a little bit of guidance because these students were asking some questions about how do you characterize the rocket engines that we're test firing. So there are a bunch of handouts from the Estes Rocket Company for these Estes solid rocket motors. Here's one of them, and it says, in general, you've got this maximum thrust that shows up, and then it goes to this level plateau for a little while, and then it peters out, all in typically less than 1 second of time. And then some number of seconds go by, and then this pop little ejection charge fires that tries to push the parachute out of the front end of the rocket engine. Nice. Okay, so they have it listed for several different types of engines. We're dealing with an an A8 engine, a B6 engine, and a C6 type engine. So we're hoping to see curves similar to these. When we go to Logger Pro, here is some data for the B engine. You need to get Logger Pro and install it and then open the data files. If you click and drag on a region, you can zoom in on it. Recognize that this moment here is listed as so many seconds of time. In this case, 0.90 seconds is where the cursor is. And then over here, this is the beginning of that ejection charge. And when you click on that with your cursor, it says, oh, now you're at whatever it says. Interesting, 4.294 seconds, I guess. So maybe I wasn't reading the first one correctly. So right now, my cursor back here, is that changing? Yeah. So the cursor right now is at 0.90 seconds. And now my cursor way over here in front of the second peak is at 4.28 seconds. And so by subtraction, you can calculate how much time has gone by from the end of the thrusting to the beginning of the ejection curve. Okay, now I'm going to zoom back out and say another thing you can do is you can maybe zoom in on just this little region here. Now it goes off scale. Okay, and look at the peak value. So the data tables in Logger Pro say, oh yeah, the peak must have been right there at 14.010 newtons is what it reports. And how does that compare to the chart? Another thing you can do is integrate the area under this curve. So they have ways of doing that, right? Maybe that's this one. And it says the integral under the curve is 4.417 newtons times seconds. So that's how you determine the impulse. Impulse is the area under the curve. I'm sorry, I keep zooming in incorrectly, don't I? Okay, so and then how do you get the average? Well, you take the impulse and you divide it by the time duration, and that will give you the average force. So when you do this assignment, I was hoping that you would go to the chart that is labeled the Estes engine chart, look up the data for each of the three types of engines that we have. For example, the A8-3 engine. And then there's only four numbers. Well, there are four numbers here that you can compare. You can compare the total impulse listed here to the total area under the graph for the engine firing. You can compare the time delay in seconds here to the time delay observed on the Logger Pro data. You can't do anything about the maximum liftoff weight because we don't have enough information. For the maximum thrust, you can compare this value listed in the table with the peak value that you see in the Logger Pro data. For the thrust duration, you can compare the value listed in this table with the duration that you observe in LoggerPro. We did not weigh the initial mass of the rocket engine before or after it fired, so we do not have enough information to calculate what was the initial weight, propellant weight compared to this table. But there are these four variables, four values that you can determine for each rocket engine using LoggerPro. Total impulse being the area under the curve, time delay observed on the graph, thrust, peak value observed on the LoggerPro data, thrust duration observed on the LoggerPro data. In doing a comparison between observed and accepted, this table would be considered the accepted value, and the values that you observed are considered the experimental values. A reminder that the formula for calculating percent error is to take the experimental value, subtract from that the accepted value, divide all of that by the accepted value, and then multiply it by 100%, and that gives you your percent error.